What if I told you that, right now, we're picking up a message from a star that's already dead? It's not science fiction. It's a real-life cosmic ghost story, and we're just starting to figure out what it means.
So let's set the scene. We're looking out towards the heart of our galaxy, the Milky Way, into the constellation Sagittarius. We're talking about a distance of 7,000 light-years. That's so far, the light we're seeing tonight left that star when humans were just starting to build the first cities on Earth. And from all that way away, through all that time, something is reaching us. A pulse, a steady, rhythmic beat. It's a message from the collapsed corpse of a star, and believe me, it's carrying a secret that's making us rethink a lot of what we thought we knew. Okay, let's dive right in. The thing sending this message is what astronomers call a pulsar. And the best way to think about a pulsar is like a cosmic lighthouse. It's spinning at an insane speed, and with every single rotation, it sweeps a powerful beam of energy right across the galaxy. So, here's how you make one. You take a star, way bigger than our sun, let it run out of fuel, and it collapses in on itself with incredible violence. What's left behind is a super dense ball called a neutron star. Now, if that dead star is spinning and has a strong magnetic field, it blasts out these beams of radio waves from its poles. And if we're lucky enough to be in the path of that beam, tick, we see a pulse. So let's meet our ghost star. Its official name is PSR B1749-28. It's our lighthouse, about 7,000 light-years away in Sagittarius. But here's the kicker. The real challenge? Look where it is. It's barely 1 degree away from the galactic center. That's like trying to hear a whisper next to a jet engine. It's one of the noisiest, most chaotic parts of the entire sky. So why is that so hard? Well, it turns out the space between us and that pulsar isn't empty at all. Not even close. It's full of what you can basically call cosmic fog. And on top of that, there's a ton of background static, like a radio station that just won't tune in right. And this slide just nails the problem perfectly. On the left, you see what a pulse from a nearby star looks like. It's sharp, it's clean, it's obvious. But on the right, that's what happens when a signal travels 7,000 light-years through all that cosmic gunk. The sharp pulse gets smeared out, scattered, and delayed. It becomes a blurry mess that's incredibly difficult to even find. So you're really fighting a war on 3 fronts here. First, there's that cosmic fog, the interstellar medium which just scatters the signal all over the place. Second, there's the galaxy's own background hiss, which is loudest right where our pulsar is located. And to top it all off, our own planet's atmosphere, the ionosphere, jumps in and adds its own layer of distortion. It's a real mess. And look, don't just take my word for it. Scientists have known about this for a long time. This quote from back in 2011 basically says, yeah, trying to find a pulsar in that part of the sky at low frequencies is a nightmare. For decades, most astronomers thought hearing a clear pulse from B1749-28 was pretty much impossible. But then, things started to change. We got better tools. We built brand new eyes, a whole new generation of radio telescopes that were designed for one purpose, to peer right through that fog and listen through all that static. And this table just shows you what an incredible leap we're talking about. Compare a telescope from the 60s to a modern one like LOFAR. Yeah, the collecting area is bigger, which is nice, but look at the bandwidth. It's a 48 times increase. That is the real game changer. It means you can slurp up so much more data at once, which is absolutely critical for finding these incredibly faint signals. So how do these new telescopes work? Well, it's pretty genius. Instead of one massive, expensive dish, they use thousands of smaller, simpler antennas spread out over a huge area. Then, a massive supercomputer takes all those individual signals, digitizes them, and combines them perfectly to create one enormous virtual telescope with incredible power. Okay, so let's recap. We have our target, the lighthouse, B1749-28. We have our problem, all that cosmic fog and static, and now we have our solution, these powerful new telescopes. The stage was set for a major discovery. So, the big question is, after all that work, after building these incredible machines to cut through the noise, what did they find? What was the message that this ghost star was actually sending us? And this is where the story takes a fascinating turn. They found it. They detected the pulse, but it was weird. It was shockingly faint. See, based on how bright it was at higher frequencies, scientists had a very clear prediction for how bright it should be at low frequencies. But what they actually saw was 10 times dimmer. The lighthouse was on, but it was way, way fainter than it had any right to be. And the scientific paper that announced the discovery says it all. The signal was an order of magnitude lower than predicted. Now that's science speak for, whoa, this is 10 times weaker than we expected. This wasn't some tiny rounding error. Something was fundamentally different about this pulsar, and none of our existing models could explain it.
So, of course, there's a technical name for this mystery. It's called spectral curvature. See, most pulsars follow a simple rule. They get brighter as you go to lower radio frequencies. But pulsars like B1749-28 break that rule. Their brightness curves over and takes a nosedive, getting way fainter where they should be getting brighter.
Okay, so you might be thinking, all right, one distant dead star is a little dimmer than we thought. Why is that such a big deal? Well, it's a huge deal, because that one faint pulse starts to pull on the thread of some of our most basic ideas about how these incredible objects actually work.
Because here's the thing, B1749-28 wasn't just a one-off weirdo, it was a clue. What scientists once thought was a rare quirk might actually be incredibly common. Newer studies are now suggesting that more than a fifth, 21%, of all pulsars might have this same strange dimming effect. We were only seeing the tip of the iceberg.
And this is really why it all matters so much. That single observation of B1749-28 forces us to go back to the drawing board. It challenges our models of how pulsars even create radio waves in the first place. It suggests that the cosmic fog between stars has more going on than we realized. And most importantly, it proves that if we ever want a complete map of all the pulsars in our galaxy, we absolutely need these powerful low-frequency telescopes to find all the quiet lighthouses we've been missing.
So in the end, the faint beat of PSR B1749-28 wasn't the message we expected. It was a puzzle box, delivered across 7,000 years. It's this beautiful reminder that every single time we build a new way to look at the cosmos, the universe finds a way to surprise us, to show us something that wonderfully complicates the entire picture. It just leaves you wondering, what new doors will the next one unlock?